Hey everybody, this is Matt, and this is another video in the computational design series that I finally had a chance to get to. And the last time we chatted, which I'll have a link in the post, but the last time we talked, we were looking at the Modulo command and the advantages that Modulo provide from a computational perspective, and I kind of talked about being able to use mod inside nTopology for a lot of things, which makes it really powerful. But the biggest thing being patterning of custom unit cells. So what I have here is a custom block, just to show you an example. Let's just pick a sphere. I'll hide that stuff. So here's a sphere in space. And now we have this field that we can then intersect with the body. There you go. So now it's patterned. One of the cool things, there's lots of cool things about mod, but one of the cool things is it fills the space, your design space inside nTopology infinitely. Or at least within the context of about as filled as you need it to be. And then it's also really, really fast. So if I want to take and change some of the angles of the pattern, if I want to do an additional offset of the body, you can kind of create these really nice structures. I mean, what we've also done here is okay, I gotta turn rotation off. But we can also fill like a single axis or two axes, just to create a pattern that stretches but doesn't necessarily pattern in all three axes. So this is a custom block that I built, which essentially runs through the steps the same way that I'm going to show here. It also works, as you can see here with something more complicated. Here's our nice Christmas colors or Christmas looking stars, but the seed to this is just a kind of more complicated unit cell, but you can see here that it handles complicated unit cells pretty well as well. There are several tricks that you should know, which is what we're going to go through here for creating a nice robust workflow for dealing with these types of things. So kind of the background of this is, most design tools are, you're going to get a strut-based lattice, inside nTopology. That's going to be something like our volume lattice. We're going to, have a diamond lattice, and it's just going to be a strut-based lattice. The nice thing about struts are, in general, they're pretty easy to work with. We can go straight to an FEA with them, but there are some limitations mechanically to, solely a strut-based structure. On the opposite side, we have sheet-based structures, TPMS structures, those things which exhibit a very high surface area for the volume that they represent. They have a couple really cool sort of novel mechanical properties. I wanted to be able to have a way to have a hybrid between the two, but still have a custom unit cell. There is an array tool inside of nTopology. I found it to be a little bit slow for what I use it for. And again, it's limited in that you have to plan out where it's going to be. You have to array it in XYZ, whereas using the modulo commands, you can just throw the field in there of your custom unit cell and intersect it wherever you want. It's way faster. It's pretty robust. As you'll see down the line, we can remap it. We can alter the structure pretty easily. So let's sort of start at the beginning with our unit cell. You can see here we can go way back. So here I'm just building a unit cell, and this unit cell, actually, I'll go through the static analysis, is really cool. I was trying to create something, that, and I'll just go over here to show this. I was trying to create something that basically went around kind of a standard just cubic beam structure. I also wanted to create something a little bit more auxetic in nature, you know, taking advantage of a negative Poisson's ratio, as well as providing a very, very high amount of flexibility. And typical node-based lattices, right? These are going to cross in the middle. They're going to provide a little bit more inherent structure, but what we're doing here is we're creating sort of the sheet-like middle for flexibility, and then we're going to join it at each of the corners. So this is just an example. I had kind of worked with this unit cell, something similar before, so I knew that it had some pretty cool mechanical properties that I wanted to try to, to mimic. So that's one of the reasons. Again, I just wanted to make it, something that I could utilize with, basically woven with a different structure as well. So what you're going to see here is, a couple pretty integral design tips. And let's just go through and look at mod, in an axis. We'll look at the field viewer. So if we look at the field viewer for mod, you can see here that I'm using X as my first. And what you notice here that there's not a lot of info. Most of the blocks have a lot of info when they talk about it, but Modulo is a pretty well-known computational command, so it just says it first operand, second operand, not a lot of detail. But what it does, and we went over this in the last video, so I'd encourage you to watch that if you want to know more about the concept. But what you'll see here is that in a sequential pattern, we go from 0 to 10, and then atypically, most sign distance fields are continuous, but you see here we have a break where we're going directly from 10 to 0. So the good thing is that allows us to pattern within the space. The bad thing is if you do not control your cell properly, you're going to get a lot of discontinuities. And what happens when you go from 10 to 0, with this nice asymptote, is you're not really going to have a nice continuous looking field unless you are doing controlling it the right way, and we're going to go through that. So first off, we're taking our unit cell. I almost always refine its bounding box because we're going to use its bounding box here for length calculations and patterning. I almost always provide a bounding box. You can see here, in my implicit array field, I have a tolerance down here. That tolerance is linked to this refined bounding box. The more complicated your unit cell, the larger your unit cell, the longer that implicit array field is going to take, mostly due to this step. You can get away with not, but again, because it's so important that we line up the unit cell to the patterning in these mod fields, it's almost always what I do. The second step confuses a lot of people when they start working with Modulo. It confuses people when they start trying to tinker with it until they get told what the problem is. And it's this translate right here. So you can see the difference between the two fields. And what we're doing here is taking this unit cell that's at 0, 0, 0, right? It's centered, which is kind of a second portion of the step. You want your unit cell to be central, and that's just mostly to do with the fact that these commands and a lot of other fields scaled in are centered about the global origin. So build your unit cell around here. If you don't build your unit cell here, I could show you a little bit of a trick. If you've got your unit cells way out here, it just happened to be it's out off in La La Land over here, but that this is my 0 point. What you can do is you can look at the center, or in your bounding box in your centroid, and you can look at its vector. Right, this is the vector that defines its center point, and so you can take this sphere, translate it by its negative vector, which is going to pull it back to that center point. So I usually do this. This is a trick that I do with meshes, right? Sometimes meshes come in off way in space somewhere. So a good way to get them back to center is to find their vector of their centroid and grab its negative, and it pulls them back into the global origin. Again, this just allows you to be operating inside nTopology's origin, which I always find a little bit easier. It's also easier to scale and view and to rotate if you're centered to 0. So we've got a refined box. What we're going to do here is we're going to translate this by half of each of the axes lengths. So I made it a little bit simple in this example in that my unit cell is a cube. Your unit cell can be a different shape. It can be a rectangular box, let's say. We are going to be defined, at least for this, into a cubic cell and patterning. Maybe the next one I do will be going over how to use this for like hex cells, implicit hex cell, because I know that those are offered as unit cells. There are some sheet-based hex cells, but building those blocks and patterning them follow a few different rules from a patterning aspect than cubic, which is a little bit of an easier concept, which is why we're stepping through it first now. So we have this refined box or refined cell. We're translating again by, here's our vector, our axis 1, 2, 3 length, x, y, z. We're dividing those by 2, so you can see here we're moving it by 5 millimeters, which is half what our bounding box is. And that gets me here. This is, you can see here, we can go back and look at our X mod again. So somebody who understands, the engine inside nTop might have a little bit better understanding of this, but my understanding is that, why we go half is because where we're starting this mod field is at X, right, central to X. Meanwhile, our unit cell spans across X, so we're giving it, a better place to start. You probably could tinker with this, leave your cell in the middle, and rather than an X field, you could say X plus 5. That'd probably do the same thing. At least for the purposes of here, I'm just trying to make it as simplistic as possible. And so the most robust way that I found is to center your unit cell about 0, and then translate it by half of the side length using a vector. And that's going to give you, again, your seed for your field. So then we're going to perform a remap. Again, this video isn't the time to go through in detail what remap is. So I'm not, because I could ramble about it if I wanted to. So what's the patterning aspect? So we're going to say, mod in X, Y, and Z. The first operand is going to be, the axis by which you're patterning, and the second is going to be the length of that axis. So again, right now we're making it easy in that it's, a cubic cell, with equal side lengths. And what that gets us is this field here. I'll show it to you. I like turning my contour intervals on. There you go. So here's our field, where you can see here we have our, our field stepping up in Z. When we get to the top, you can see. So we've joined these in the middle. Again, this is because we've refined our bounding box. We know exactly what the side lengths are. We've translated it by a very precise number, and then we've patterned it by a very precise number. If those are not precise, you will get discontinuities here, and I can just show you that real quick. Let's say in X we decide to go 11. What that's doing is it's, we're continuing the field past where it's supposed to be. Well, I forgot I had a bunch of stuff calculating on the back end, so I'm going to Control Z that. So it's really important that your lengths match. If you're just trying to fudge some things, it will not turn out well. and you're not going to get the structure that you're kind of looking for. So again, here's the field. It's patterned. You can see here that we've got this joined nicely in the center, and it's going to do what we want it to do. The next steps after that are mostly just optionally scaling and rotating the structure. Once you have this field built implicitly, it doesn't really matter where you go. The field's going to be there, so you can just kind of fly off over here, and the field's still going to be there. So the really cool thing again about utilizing this is you're taking advantage of custom unit cell patterning, but it does not matter where you're intersecting it with. It'll just exist kind of infinitely in the space, which I think is really cool, and it's really useful. So all I'm doing is I'm going and I'm smoothing it a little bit, which I found out later it was kind of useless. I actually had a different unit cell which made a little bit more use of the smoothing. Then I scaled it, right? So we have the option to scale the unit cell. This is helpful if you build a unit cell a little bit bigger, just because sometimes it's easier to work with a larger geometry. And then again, once you have that field built, then you can scale it as you need to and rotate it. I had an option to offset it, and then here's the unit cell visibility down here. It did give me the mechanical properties I want. When we look at like a TPMS structure, if you look at it yielding plastically, it actually has a really cool sort of stress strain curve where it holds the load as it as the load is building up, and then it plastically fails, but only the first layer, and then it kind of all smushes down on the next layer, and then you'll actually see it start ramping up again, and then it'll plastically fail again. And usually that's tied to the periodicity of the structure. So you can see here when I did this, I was achieving the same effect in that we're getting displacement up here, and the displacement down below is a lot less. So we're getting a higher amount of displacement for these top unit cells. We're essentially accomplishing the same thing, which I thought was pretty cool when I started analyzing that. The other really cool thing about mod is that you're starting with a unit cell, so it really goes nicely hand in hand with nTopology's homogenized unit cell. We're getting this unit cell, we can evaluate its properties, we know kind of how it's going to deform, we have a general idea about its modulus and what that looks like. And so again, because it's built as a custom unit cell, we can then use Modulo to pattern that unit cell. After we've refined it, we've done what we want to get a really nice looking unit cell that mechanically accomplishes what we want. And then down here, you can see we've got this custom cell, which I think looks really cool. I think probably because we have these stretch joining on the diagonals that it's printable. We may have some challenges where all these circles close and some sag, but for the most part, I think that this is a printable structure. I may print it up just to see what it looks like. Again, we've accomplished our goal of having it be able to flow around this implicit beam configuration, and then here's the kind of the central portion, shown by this kind of middle foam-like structure. A couple just other random tips and tricks. I actually did these implicit beams through the same pattern or the same sequence of this modulo. One of the things I like about using modulo is you can see down here I'm creating this beam pattern implicitly. So if I want to have a little bit better or something, construct my unit cell a little bit different, I can do that. This is kind of how the implicit beams inside nTopology are created. The only reason I wanted to have a little bit more control over it is because my patterns weren't matching up, and so I created these both over here first, and I knew that they matched, so that when I did my mod field, I knew that they'd be in sequence. So the other thing that I think is cool is because it just exists as a field, it's not like an array body, which is a lot more heavy. you have the option to take this field down here and remap it further. So what we've done here is we've remapped the cell structure with some custom shapes to allow for it to, let's say, absorb or resist some sort of an impact better. So now we have the ability to remap it. I've not attempted to use this with that conformal tool that I built, but I think it would be a really cool structure to use conformally between sort of a top and a bottom surface. That would be pretty cool to see. And again, this is just a nice way to create usable structures that are lightweight, that are fast, that give the user the power and the ability to get out of what they want. So I hope that this has been informative and helpful, and I know that something that I often talk to people about as a potential option, but I do know that there are some pitfalls. So hopefully we've addressed all of those and given you guys a kind of good grounding for being able to use this in all of your guys' day-to-day work. And I'm interested to hear your thoughts, feedback, and comments. And I hope you guys have a great day.